All right, go ahead. Are we filming? All right. So sheet of rubber here, right? Concept zero, if we have a positive charge, it's going to push this sheet of rubber like that, right? Negative charges push it down, so we can have a complicated distribution like this. And then the one way other thing to visualize, right, are that these things all have equipotential, which are like the topographical lines, right? That separate these things. The other thing that can happen too, right, is that you can have the different size things, right? So if it's got a bigger surface, the drop off, the slope of this is your electric field, right? Okay, so we've got that, whereas a pointy thing has steeper slopes, therefore a bigger electric field right next to it, right? Okay, so you can think about the size of the object. We also generate uniform fields, right? We use parallel plates, right? Okay, and you can imagine that space between these, right, is it's got a uniform slope, right? So therefore it's got a uniform electric field, which is kind of cool. And then if I keep the difference in height the same, but move them closer together, it's a bigger field. That's a smaller field, right? Electric field. And then the other thing that's cool too is on the Van de Graaff, when people had their hair standing on it, and remember I pointed at it, I sprayed charge on it, right? So the question is, why does a pointy object concentrate the electric field? So put a point and if you look at this, right off that point, there's a really steep drop off, right? So the same thing's going on spatially, right? It has to do with calculus. But pointy objects like that generate really strong electric fields, and so I was charging the air, I guess, with the opposite of the person on the Van de Graaff, and those particles were flying away from my finger and hitting their hair. I think that's about all we say, right? Yeah. Okay, then we make the electromagnetic space-time collapse on itself. Ready? 1, 2, 3, drop. Oh, I love that.